Another part of being able to follow concentration with time is the half-life. Half-life is the time it takes for the reactant concentration to decrease to 1/2 of its initial value. You hear about this most likely or most often associated with radioactivity. The half-life is the amount of time for half of the radioactive material to have decayed, but you can do it for any kinetics. And so for each order of the integrated rate law, there is also a half-life equation that is derived basically by doing so. So if we say that the initial concentration of A is 2, and so therefore half of that concentration at time t would be 1, and we do the first order, then basically it's going to be the natural log of concentration at time t divided by the concentration at time 0 is a negative kT. And so I put in these 1/2 as a negative kT. When I take the natural log of 1/2, I get a negative 0.693 is a negative kT. And I solve it for t, then I have a negative 0.693 divided by a negative k is equal to t. So t then is 0.693 divided by k, which is what you see here then for the half-life. Okay, and I can do that for the second order and for the 0 order also. I need to change this up. Instead of putting numbers here, I need to put the fact that this would be basically 2 times AT or 1/2 of A naught. Either way of doing that. Actually, I want to put this as being 1/2 of A naught since I'm solving for A naught. But I can do this for either of those orders also. So here's a problem. Okay, again, in these problems, it's going to tell you that this one is a first order reaction rate, and it tells me that the rate constant is this, so K is 5.36 times 10 to the minus 4th. I can also write down the fact that it's first order if you need to. Again, it gives me a temperature because the K's are temperature dependent. Okay, and it wants to know, calculate the half-life. So it wants to know what T is, T to the 1/2. However, it wants to know it in minutes. Okay, so the equation for half-life for a first order is T is 0.693 divided by K. So I simply substitute in 0.693 divided by the 5.36 times 10 to the minus 4th. When I do that, I get 1,1292.9. That's going to be in seconds because of this unit here. So this came because of that right there. It wants it in minutes, so what I need to do is take the 1,292.9 divided by 60 seconds per minute, and I get 21.5 minutes. Okay, and so that's basically what you need to do for the first order. I also have a second order problem. Okay, again, it's going to tell me what the order is in the problem. Okay, when I expect you to know what the order is, it's going to tell you that. Again, I have a K that is 51 per molar minute. This is in minutes this time. I have a temperature because all of these are temperature dependent, but I'm not going to use it right now. I have part A, which has a starting concentration, A naught, is 0.0092 molar. It wants to know what the time is for the concentration of A at time t to go to 3.7 times 10 to the minus 3 molar. So this is just an integrated rate law because it gave me 2 concentrations. This is not 1/2 of this concentration, so it's not a half-life. So I need to do the integrated rate law. So for A, the integrated rate law for a second order is 1 over concentration at time t is kT plus 1 over the initial concentration. So I have 1 over 3.7 times 10 to the minus 3 is 51t plus 1 over 0.0092. I'm going to take the inverse of this, and when I do that, I get 270.3. It's still 51t plus, when I take the inverse of this, I get 108.7. So I need to subtract. I'm going to isolate this, so I need to get rid of this plus. The opposite of plus is minus, so it's going to be 270.3 minus 108.7 is 51t. When I do this, I get 161.6 is still 51t. Now this is 51 times t, so the opposite of times is division, so I'm going to take 161.6 divided by 51, and that gives me t. So my t is equal to 3.17 minutes. And it's in minutes because of the fact that this is in minutes over here. Okay, so that's A. B says it wants me to calculate what t to the 1/2 is. Okay, so this equation is, I'm going to change colors so it's a little obvious so I don't mix these up. So this is t to the 1/2. Let me just erase that. T to the 1/2 is what we're looking for. We're still going to use this initial concentration. The formula for t to the 1/2 for second order is t to the 1/2 is equal to 1 over k times the initial concentration. So it's 1 divided by 51 and 0.0092. Okay. When I multiply these two together, I get, oh, no, don't know where I am now. Really, really went far. There we go. That's the problem with being down here at the bottom. I get 1 divided by 0.4692, I believe. I can't read my handwriting. 2. I'm going to move this over here because I'm running out of room. And so 1 divided, so the t to the 1/2 is equal to 2.13 minutes. So there's one answer. Oops, wrong one. This is the other answer. This is for A. Okay. And so this one has both the integrated rate law and the t to the 1/2 problem in it, both. And this is the end of part 3 of the video series.